Okay, welcome to part 2 of the Structures of Molecules laboratory. We're going to be looking now at methane gas. That's CH4. It's an interesting molecule because there's one carbon atom in the center, 4 hydrogen atoms on the periphery. So let's take a look at the Lewis structure first. Remember that each of the hydrogens brings to the structure 1 electron each. I know that because the hydrogen from previous examples is in the first column, and it brings 1 valence electron or 1 electron to the structure. There's 4 of them, so that they will bring 4 electrons to the structure. Carbon is in the 4th column on the periodic table. It will bring 4, so 4 plus 4 is of course 8. So let's place those in. So I'm going to place these two just to connect this carbon with this hydrogen in this covalent bond here, these two here, these two here, and these two here. Well, that's a total of 8, isn't it? So I've placed all of my 8 electrons now, and what's more important is that the carbon, the central atom, has an octet of electrons. It has 8 electrons surrounding it. The hydrogens, remember, do not require the octet. They require only 2 electrons around them. So this looks like a perfectly viable Lewis structure. And just by looking at the structure, it's pretty clear, to me at least, that this is a symmetrical molecule. How do we translate then? How do we translate this Lewis structure into a 3-dimensional structure? Well, it's going to look something like this. Carbon in the center, 1, 2, 3, 4 hydrogens on the periphery. They're going to be pushed as far away from each other as possible. Remember, that's called valence shell electron pair repulsion theory, or VSEPR. And when you look at it from a 3-dimensional point of view, you can really get an appreciation for how symmetrical this molecule really is and what that means in terms of its shape. We call the shape tetrahedral. Tetra meaning 4, 1, 2, 3, 4 atoms surrounding the central atom. And now let's look at the electronegativity difference of a specific bond. Let's take this bond, for example. We could have taken any of them because they're the same bond, but the electronegativity difference between them is hydrogen is 2.1, carbon 2.5. I can see that from the electronegativity table. And the electronegativity difference then is 0.4. Above, at least slightly above the 0.3, these are all polar bonds, at least slightly polar bonds. So the bond polarity then would be polar. But look what's interesting about this molecule. Even though the molecule has 1, 2, 3, 4 valence electron, 4 atoms around it, and those 4 atoms are these 4 bonds that are connecting these atoms are all polar, the molecule as a whole is nonpolar. Why is that? Well, it's nonpolar because you think of each one of these interactions, each one of these covalent bonds as a tug of war. We've all played tug of war as children. Each one is a tug of war. So the tug of war is going on here, and there's a winner. There's a clear winner. Carbon is more electronegative than is hydrogen, and so carbon wins this tug of war. Carbon wins this tug of war, and so forth. But the tug of wars are exactly balancing each other. So because of that, because they exactly balance each other, there is this symmetry to this molecule. And the symmetry means that the molecule as a whole is nonpolar. The molecule as a whole is symmetrical. Even though the electron distribution in this bond, for example, is not symmetrical, electrons being kind of more predominant in this part of the bond, or this part of the bond, than this part of the bond. Same thing here, this part of the bond being more electron dense than this part of the bond, because as we look at the entire molecule is symmetrical and therefore nonpolar. So that's methane. Now the next one is a slight deviation from methane, and that's methyl chloride. And you'll notice that in methyl chloride, one of the hydrogens has been replaced with a chlorine. I'll do that now. One of the hydrogens has been replaced with a chlorine. So this is the structure. It looks very similar to the structure that we saw before, with the exception of that hydrogen. But let's look at the electron structure, the Lewis structure for this molecule. Each of the hydrogens will contribute 1 electron because it's in the first column. Carbon will contribute 4, and chlorine will contribute 7. So 3 plus 4, that's 7, plus an additional 7. That's a total of 14 electrons. Well, let's place them. 2 here, 2 here, 2 here, and 2 there. That connects all of the atoms, but I've still got 6 more to place. Don't place them on the hydrogens. They don't require octets, but chlorine does. 1, 2, 3, 4, 5, 6. Let's ask the question then, does chlorine have an octet of electrons? 2, 4, 6, 8. Indeed it does. Chlorine has 8 as well. 2, 4, 6, 8. Looks like it's a very viable structure, Lewis structure, and we'll translate then into the three-dimensional structure. The fact that the chlorine has replaced one of the hydrogens doesn't change the overall structure. Valence shell electron pair repulsion theory still requires that these electron densities still be as far away from each other as possible, so it's still a tetrahedral shape. It's still a tetrahedral shape, okay? So let's look at each individual bond. We're going to distinguish now this bond or this type of bond from this type of bond. In this type of bond, the carbon-hydrogen bond, the electronegativity difference is 0.4. 2.5 minus 2.1 is 0.4. Slightly polar. We saw that in the last example for the methane. But for this bond right here, carbon and chlorine, the electronegativity difference is 0.9. Both bonds polar. This one, as compared to this one, is not as polar. Okay, so these are both polar, but this bond here is less polar than this bond. In other words, there's a greater difference in electron density between this atom and this atom than between this atom and this atom. The bonds are polar. The molecule, this time, unlike the methane, also polar. Why? Well, it's not a symmetrical molecule. When hydrogen was here, the molecule was completely symmetrical. It didn't make any difference how I turned it. It was the same molecule. 4 hydrogens surrounding a central carbon. But now I've replaced one of those, and now what happens is that this renders this molecule non-symmetrical. In other words, the molecule is polar. We come to now the final structure for a laboratory, oxygen gas. I'm sorry, this is not the final structure. We have a couple more. Okay, but we'll look at oxygen. And oxygen is also very interesting. Oxygen is a diatomic molecule, and oxygen, because when I look at the periodic table, contains a total of 6 valence electrons. 2 times 6, 12, so let's place them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We see immediately that there's a problem, and that is I've run out of electrons. What I want you to know from this laboratory is that when that happens, the remedy is to try multiple bonds. Try a double bond. We now know this is wrong. So let's try a double bond at the center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That seems to have remedied the situation perfectly. Let's look at this oxygen, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. It's a perfect Lewis structure. We've now got the Lewis structure for oxygen gas. Let's transform that now into a molecule. So let's take a look at this right here. I'll construct this oxygen molecule by placing 2 of these. Tell you what, let's do this. We'll now consider these to be oxygen. And we'll put a double bond here, just like that. And I'll need another oxygen. So I'll put another one right there, just like that. And now what I need to do is take care of these non-bonded pairs. So I'll put a lone pair there, a lone pair there, a lone pair there, and a lone pair there. And I've got the structure. A double bond, I'm going to push these 2 atoms a little bit closer together because the double bond, remember, is going to be a stronger pull. I've got more electron density in here now than I did before with a single bond. The nuclear charge, that positive charge from the nucleus of each atom, pulling them together is going to shorten this double bond relative to the single bond. So this is the structure. It's a linear structure for obvious reasons. Anytime you have 2 atoms involved, and only 2 atoms, it's going to be a linear structure. What's the electronegativity difference? Simple. Oxygen has a high electronegativity. When I look on the electronegativity chart, it's 3.5. But 3.5 minus 3.5, electronegativity difference, 0. No electronegativity difference. Therefore, the bond is polar. There's no electron buildup on this side of the bond or this side of the bond. It's perfectly symmetrical. Well, what about the molecule? Also nonpolar. No matter how I turn the molecule, if I look on the left and I look on the right, they are identical. They are identical left and right. So we've got a nonpolar bond nonpolar molecule. That's oxygen gas. Let's look at nitrogen. Nitrogen gas also diatomic. Nitrogen gas is also diatomic, and nitrogen gas is also very interesting. I'll use the same colored spheres for this one right here. And this time, when I look at nitrogen, each of the nitrogens will contribute 5 electrons. And I see that it's in the 5th column, so 5 electrons. So let's try a single bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If there's 2 nitrogens, each one of them contribute 5 electrons, it's not going to work. There's not enough electrons to give this nitrogen an octet. So that's a wrong structure. And we know from experience that when we've got that situation, we're going to try multiple bonds. Let's try a double bond. Go up one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same situation. I'm not getting an octet on this one right here. Even if I had these electrons over here, I still wouldn't have an octet. I'd have only 2, 4, 6. So this is a wrong structure. Let's try that again, this time using a triple bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like I've got a viable structure. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It looks good. That looks like a good, solid structure, electron dot structure, and I'll use that structure to build my molecule. This time, though, I'm going to have 2 nitrogens connected by a triple bond. Not a double bond, but a triple bond, just like this. So I'll put 3 toothpicks between these 2 atoms right here, and I'm going to really make this a short bond because triple bonds really have a high attractive potential between these 2 atoms because of the nuclear charge. I'm going to push those far apart. Remember that I do have those lone pairs on the end, so I'll put those like that. This is still, though, a linear molecule. Nonpolar bond, nonpolar molecule, and that's the structure right there, linear. And now we come to the final structure. It's CO2, carbon dioxide gas. CO2 is composed of 3 different atoms, carbon and 2 oxygens. Carbon pulls in or contributes 4 electrons. It's in the 4th column, oxygen 6 each. So that's a total of 16 electrons. Let's put them in. 1, 2, 3, 4. That connects the structure. 4 out of the 16 have been designated. Let's do the other 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a problem. This oxygen has an octet, that carbon has an octet, that oxygen doesn't. How do we remedy this situation? For our experience tells us, try double bonds. Whenever possible, we're going to make them symmetrical. So I'm going to put 2 double bonds, 1 right there and 1 right there. That distributes 2, 4, 6, 8 of the 16 electrons. Now let's do the other 8. How about 2 there, 2 there, 2 there, and 2 there. Notice I kind of put them out to the edges here, 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 and here to kind of show the valence shell electron pair repulsion theory idea that electrons are going to be as spread out as far as possible. Let's look at that structure now. The structure is this one right here. I'm translating this electron dot structure into this 3-dimensional structure. We have carbon in the center, oxygen here, double bonds between these 2. Let me push these in a little bit tighter, just like that, because I want to show that double bonds are shorter than single bonds because of the increased attractive force. And a lone pair here, a lone pair here, those correspond to these 2 lone pairs. Lone pair here, lone pair there, that one, that one. The electronegativity difference between these 2 atoms is exactly 1.0. That's above 3.0, making this a polar bond. This is a polar bond with a greater a greater electron density in this atom as opposed to this atom. More electron density here on the peripheral part of this bond than here. Same thing here. More electronegativity on this atom than this atom, so more electron density in this part of the bond than this part of the bond. Notice this is a polar bond. This is a polar bond, and this is a polar bond. However, like we saw with methane, these 2 tug of wars are going to cancel. Let's take a look at our Lewis structure once again. these two structures are going to cancel so that the electronegativity is directed towards the oxygen here, is directed towards the oxygen on this side, like that, but they cancel each other exactly. So we have a polar bond, but a non-polar molecule. Okay, I hope that makes things a little bit more clear now. Thank you, and I will see you on the next laboratory. Thank you. Bye-bye.